All right, grade 12s. So some people have been sending me questions about how to do the homework. It's great that you need me. Okay, so listen, I'm going to help you do a couple of these. There's one that I didn't get to in the notes yet, so I'll try to explain that. Okay, my writing's going to be a little weird too because the tip on my pen here is starting to wear down. I'll have to order like new pen or new tips. I haven't used this laptop that much, but since the pandemic, I use it all the time. All right, so look, one of you asked this question number 4 here, okay? And what I'm going to do is I'm just going to show you how to do it right here on the diagram. It says calculate the magnitude and direction of the electric field at point Z. Now point Z, okay, is right. That should be a little bigger here. Erase that. Point Z is right there. Okay, so that's point Z. Now I'm going to draw a little box here. Okay, I'll zoom in. So listen, what you do when you're doing electric fields is you just move the microphone a little. What you do is you pretend that you're putting a little positive charge here. So you put a little positive charge there. And then what you do is you use the formula for figuring out electric fields in the proximity of a point charge. Okay, and then when you put your little imaginary positive charge, okay, just ask yourself what direction would the forces be on that charge because of these two other charges. All right. Now I'm going to call this charge over here, the positive one, call it A, and I'm going to call the negative one B. Okay. So there's charge A, and actually, you know what? I'm going to change what I just said because I just realized they put letters there. I'm going to call this one X. It's already called X. Okay, the point is called X. We'll call this one Y. Okay, so this charge is X and charge is Y. Okay, now charge X is a positive charge. So what that's going to do, I'll use the color red for this. What that's going to do is that is going to push away my little positive charge that I put, a little imaginary positive charge that I put there at point Z. The blue charge, though, is a negative charge, and so that blue one is going to attract my little imaginary positive charge. So I've got these two vectors in opposite directions, right? Okay, so now that you see those two things, now we just have to go ahead and use the formula. So to find EX, it's going to be KQX divided by RX. I told you my pen's not working very well. Divided by RX squared. Okay, so that's QX. Or sorry, E, that's field X. Now I can put these numbers in. K is always 9 times 10 to the 9. The charge X was 50 microcoulombs, so I go 50 times 10 to the negative 6. Okay. And then the distance from my imaginary charge here all the way over to charge X is the sum of those two numbers, 0.45 and 0.30. That adds up to 0.75. So I go 0.75 squared like that. Okay. And then I get a number. Now, this time I have my calculator here. So what I'm going to do is do the calculation for you. And that calculation, 9 exponent 9 times 50 exponent 6 negative divided by 0.75 squared equals, I get 800,000 newtons per coulomb. Now that one is west, okay? Or if you want left and right, it's to the left. I'll just say west, okay? Now, what about the other one? Well, the other one, EY is going to be an attractive force, okay? Oh, I'm sorry. I got the direction wrong for X. This one's east, pardon me. I'm sorry, I didn't mean to confuse you. All right, so now the other one is definitely towards the west. If you look, the red one is towards the east and the blue one is towards the west. So the red one is the repulsive force, the blue one is the attractive force. Okay, so I'm going to go KQY over RY squared like this. So that's going to be 9 times 10 to the 9. And this one's 10 microcoulombs. Never put the negative sign, remember that. So times 10 times 10 to the negative 6, like that. And then the distance is, I believe, 0.3, right? So it's 0.3 squared. Okay, then I take out my calculator. I just go ahead and do it. 9 exponent 9 times 10 exponent 6 negative divided by 0.3 squared, and I get 1,000,000. So this is 1,000,000 Newton per Coulomb west. All right, I got 800,000 east, 1,000,000 west. So when I find the net field at point Z, it's going to be, I'm going to define west as positive, so it's going to be 1,000,000 minus 800,000, right? So, oops, did I write that? Yeah, I did that right. Okay, minus 800,000. Well, that's just 200,000 Newton per Coulomb to the west, okay? Or if you like, to the left, okay? And that's it. So here we have these two charges. They both produce a field, okay? And the net effect on our little positive test charge that we put at this spot at point Z is that you have to, you know, they're going to pull in opposite directions. So we just have to subtract their fields. Okay, and we'll just use the formula to find the fields. Honestly, I know these questions seem strange, but once you get your head around what you have to do, you're just using equations, like, you know, and since it's kind of an open book what we're doing now, it's pretty straightforward, okay? All right, so that's how you find the field at point Z. Now, someone asked me about question 6 and question 7. We didn't talk about parallel plates. Okay, so question 6 and question 7. So let's spend a moment. We're going to spend a lot of time next week talking about parallel plates, but let's just spend a moment right now talking about the parallel plate apparatus. It looks something like this. Okay. Now, what are we looking at here? Well, we're looking at two plates, and literally plates, like a dinner plate. Okay. Unlike a dinner plate, these ones are made of metal and not some kind of ceramic. Okay, so these are metal plates. Okay, and it's really easy to build a parallel plate apparatus. You just take a wire, touch it to that metal plate, attach that to the positive end of a battery, take another wire over here, attach it to the negative plate, attach to the negative terminal of the battery. What will happen is charge will accumulate on the plates, and as the charge accumulates on the plates, you get a field that forms inside the plates. Now, the thing about parallel plates is here where all the lines are straight. I'm going to shade this region in here, where all these lines are straight in here. Actually, you know what? That looks confusing. So let me highlight it in yellow. In this zone in here, okay, that I'm just highlighting in the yellow zone, that yellow zone, okay, the field is perfectly uniform. Well, at least it looks that way here. Uniform. Okay, so in other words, the field strength is the same intensity everywhere. Okay, now what that means is, let's say I put my little positive here. Let me zoom in on these plates. Let's say I put my little test charge right here. Okay, there's my little Q. Or here, we'll call that point A. Whatever, I erased my highlight, but whatever. Okay, call that point A. We'll call this little test charge here, is that point B. We'll put another one here, dead center. That's point C, and we'll put another charge there. Okay, actually let me fix that so it's consistent. Okay, so here's one at point C. Now here's the thing. The field, E, A, E, B, and E, C, they're all the same. Okay? So because it's uniform, it means that the field is the same everywhere. Okay? So EA equals EB equals EC. It's all the same. Okay? Now, we're actually kind of used to uniform fields because, like here, picture gravity near Earth in your room. I was going to say in the classroom, but we're not in the classroom. So in the room you're sitting in right now. Now in your room you have the ceiling up here. and you have the floor down here. And here's you right there, okay? Now, here's the thing. Gravity, let's say you were to test the gravitational field in the room. And what you would do is you would take a mass in your hand, let's say, and you notice that there's a force of gravity pointing down towards the floor on that mass, and its intensity is 9.8 newtons per kilogram, okay? Now, this is gravitational field intensity, so it's not newtons per coulomb like it would be with charge. It's newtons per kilogram because gravity varies with mass, right? Now, here's the deal. Anywhere you test it in the room, you would get the same exact number. In other words, you could hold that mass up high near the ceiling, okay? So that is a uniform gravity field. And you would get, in other words, you would always get 9.8 newtons per kilogram. 9.8 newton per kilogram. And the direction is down. Now, it doesn't matter where you test it. You could test it near the light bulb at the top of the ceiling. You could test it near the floor. You could test it in the middle. Doesn't matter where. You're going to get the same number every time, okay? So what's the key point I'm trying to make here? The key point is inside these plates, you get a uniform field, okay? So it's the same everywhere. Now, that field with parallel plates only depends on two things, okay? I gotta make sure I get this correct. It depends on how much charge is on the plates. I think it depends on the charge separation. So, just let me verify what your book says. All right. Sorry, guys. I just want to make sure I'm not inconsistent with the book. Later, we're going to do a formula for this. But what I'm doing is just scrolling through the textbook questions just to make sure, because I think question 7 is based on these exact things. All right, so pardon the delay. Just give me 1 second. And while you're waiting, I hope you're all doing well during the pandemic. I've had kind of an embarrassing week filming that Let It Go video. It's not really ready yet. I'm kind of like, I don't know if you'll ever see it, to be honest with you, but anyway. All right, so look, so just reading what it says here in your textbook, I'll just read it word for word. Okay, what the field depends on. Okay, depends only on the magnitude of the charge on each plate. Okay. Now, so like it says the magnitude of the electric field at any point between the plates depends only on the magnitude of the charge. Now, here's the thing they don't tell you, that the magnitude of the charge itself does depend on the separation of the plates and the voltage across the plates. Okay, but the point is it only depends on magnitude. Okay, that's all. Okay, magnitude of the charge on the plates. Okay, so getting back to the notes here. So this field depends only on the magnitude I'm going to say of the charge density on the plates. That's what it depends on. Okay, so like so much charge per unit area, like coulombs per square meter of plate. Okay, so anyway, that's it. All right, now let's get back to these questions. Okay, so to answer question 6, and we'll talk more about electric fields later. Okay, I know you're excited, you want to get it all now, but I don't want to give it to you on the weekend, so I'll do it on Monday. See, the electric field midway between, okay, so if you read this question, the electric field strength midway between oppositely charged parallel plates happens to be 3 times 10 to 3,000 newtons per coulomb. What's the magnitude midway between this point and the positively charged plate? Well, the thing is, it's a uniform field. So the field is the same everywhere. So if you're going to answer question 6, since the field is uniform, the answer can only be newtons per coulomb. It's like saying, okay, that the gravity in the middle of your room, okay, right between the floor and the ceiling, is 9.8 newtons per coulomb, right? So what would it be if you put it closer to the ceiling? Okay, well, the answer is 9.8 newtons per coulomb. What would it be if you put it closer to the floor? 9.8 newtons per coulomb, right? Or newtons per kilogram, pardon me. This electric field is uniform, same. So it doesn't matter where you put it between the plates. It's 3,000 everywhere because it's uniform. Okay? All right, now number 7. It says the parallel plate apparatus in question 6. What would the electric field intensity be if half of the charge were removed from each plate? Okay? Well, the thing is, changing this will not change anything. Like on paper it would, depending on your apparatus. But in principle, if the only thing were to change were the charge, okay? So if half the charge were removed, then what would happen is, okay, and you would do that by lowering the voltage. If half of the charge were removed, then what happens is you would get half of the field, okay? So since the field is proportional to the charge per unit area, okay, then if half of the charge was removed, you'd get half of that, right? So therefore the new field would be 3,000 divided by 2, which is 1,500 newtons per coulomb. Okay, and that would be the new uniform field. So there you go, guys. I hope that was helpful, and we will talk to you again soon.